So in this part, I want to talk about in greater detail how the contact rate in an epidemic model is established mathematically. In other words, how do you put in the math terms the number of new infections? You have an epidemic spreading out. How do you basically model the number of new infections per unit of time? In our spirit of starting with the simplest possible setting, which by default will be the least realistic one, let's talk about only two types of people in a disease that spreads, in an infectious disease: the susceptible and the infected. The word susceptible, it's not to be confused with healthy. Sometimes I myself sometimes make this mistake to pinpoint, and I call them healthy, but not everybody who is healthy can get a disease, right? I mean, you can be healthy and immune already, recovered with immunity, for example. You could be vaccinated, and so on. So susceptible means that you are healthy now, but you are otherwise susceptible, as the name implies, to the disease. So that means you can basically get sick, or to be more precise, you can basically acquire the infection if you have contact with an infected person. And get used to these notations, because the more you repeat them in your mind, the easier it gets to become kind of an automatic thing. When you see the notation S, that you remember that denotes the susceptible, I denotes the infected people. There are variations of the notations, but you typically the S is reserved for the susceptible people. And let's assume for simplicity that the disease that we're going to talk about provides no immunity. So that means after recovery, you become susceptible again, like instantly, which again is not realistic, but for the purpose of making the math simple, we do that. And let's say there is no disease mortality, or basically a disease that you don't care about unless the symptoms are bad. So no disease mortality. And let's call N of T the total number of people. So if we have the people split in just two categories, then N of T is the total number of people at time T. Later on, remember, we can drop off T for convenience. Just remember not to confuse what's a constant with what's something that depends on T. Okay, so before we actually come up with the model in how to model the disease, let's talk about the contact rate. I mean, how do you put into math, for instance, how many people are infected per unit of time? Let's say T is measured in days. Usually, the way to think about, and one of the easiest way to think about in the beginning, is to think about the number of new infections. So think about the number of new infections from the point of view of an infectious people, of an infected person. There's I of T of them, right? So at a given moment of time, I have I of T infected people, S of T susceptible. But let's focus on one average or one typical infected person. Well, this person, and there are lots of assumptions that go into this, right? So for example, one of the main assumptions for what I'm going to show here is that let's assume that the population is well mixed or homogeneous. Basically, you imagine that the population is basically so close together and moves in such a way that there's basically an equal probability of meeting any person in the population. Which again, whether it's realistic or not, it depends on the context. For example, a close-knit community like a campus, where a group of people are so close together, they interact with pretty much anyone else, so therefore there is an equal probability chance of meeting any person in the population. So this infected individual per unit of time, let's say he makes contact with a fraction f, so that's a fraction between 0 and 1 of the total population, n of t. Then let's say for each of these contacts with a fraction of the total population, the probability that each of the contact is with a susceptible is obviously S of t over n of t. So at a given moment of time, you have S of t susceptibles. So the ratio between the susceptible and the total population is the probability of actually meeting a susceptible. So you have to understand that that infectious individual, when he is in the population, he will make contact, because he will not know, right? I mean, assuming he's blind to the infectious status of whoever he or she meets, right? So he's going to make a contact with a fraction of the total population, but each of these contacts, there's a probability of those contacts to be susceptible is S over n. Then there are lots of other hypotheses that play a role here. You will see it will simplify in the model, but you can basically add lots of tweaks to this contact rate. Not every contact results in infection. So for example, by contact, maybe we mean close enough that that person interacts. For example, saying hello. Now you can say hello from 10 feet, you can say hello from 1 foot. So therefore, not all of these contacts, whatever that means in the context of the disease, is going to be close enough to cause, to give a chance for the infections to be transmitted. So let's say you add the probability that each contact is close enough for infection to occur. And so let's say that probability is P1 between 0 and 1. Even in that case, if you're close enough, that doesn't mean the infection happens, right? I mean, there's also a chance maybe you didn't cough at that moment. There is no source of infection in that second, so the person who is exposed gets lucky. So therefore, we have a further reduction probability of the contact rate. So the probability that transmission occurs. And let's say that's P2. So there's lots of things that come into play in these contact rates, as you'll see, right? I mean, at the very least, you can think about, again, the fraction of people you meet, probability of that's always S over n, that you meet a susceptible, whether you're close enough, whether the transmission occurs, so on and so forth. And it's very specific to the disease, obviously, because it depends on how the disease is transmitted. That defines what you mean by contact rate. Now, since we do theoretical modeling, we're not going to dwell too much into this, but it's important to imagine and understand that the what you call these words in real life or what they mean in real life, close enough, that completely depends on the context of the disease itself. Like, for example, in a sexually transmitted disease, obviously close enough means sexual intercourse. Respiratory disease, close enough could mean really, literally distance between two people. Okay, so we have that single infectious individual, so that one infected person cause the following number of new infections. So you have basically the multiplication of all these guys, right? So you have the fraction of the people that infectious individual meets multiplied by the probability of meeting a susceptible, multiplied by the probability of the contact being close enough, multiplied by the probability for the infection to occur. It'll get much easier than that, so don't worry. I just want to know where these terms come from. Basically, I want to explain where these terms come from. So this is what one infectious person produces or causes. So one infected person causes that many number of new infections. Now, how many new how many infected people are in the population? Well, there are I of t of them. So I of t infected people then will cause that many, which corresponds for one individual, times I of t. So I of t times f times n of t, s of t over n of t, and some reduction probabilities depending on the context. So I want you to notice that in this case, the total population will cancel. And you have a bunch of constants. I have 3 of them here, but there could be more than that if you have other hypotheses. And they don't even have to be constant. I mean, we'll have time to discuss maybe later how complicated things can get, because to have these probabilities given by a constant is really the simplest possible setting, because I mean the probability may change dynamically, for instance, in time, or depending on the population size, because people react differently, right? Social distances may, policies may cause these probabilities to change on the fly, so to speak. But at the very, I mean, in the simplest setting, these are constants. And if you assume them to be constants in the model, you can lump them into a single constant. So I can basically have this contact rate regrouped so that all these constants come together, and then you have just S and I. S of t, I of t, but remember we can drop of t and I of t, the argument t, just for convenience. So all these constants lumped together, we can call them some other, usually Greek letter, right? So lambda or beta. So when you see in the model lambda is I, these are kind of the hypotheses that come into play. So I took my time here because, again, in order to really understand these models and to understand the huge limitations, and especially in the context with the COVID pandemic, with the current pandemic, with the coronavirus, I think many people misunderstand how these models are built. So it's important to understand how many hypotheses basically go into a single term, right? So I mean, you put that model into an equation and you have lambda and you call lambda an infection rate, but there are countless of hypotheses already made in that lambda, right? I mean, you will have to make some, first of all, you'll have to make a hypothesis on how people mix, and that's a huge hypothesis you'll see immediately, namely that the population is well mixed. So namely that, you know, everybody has a chance to meet anyone else in the community. Obviously, if you make a model at the level of a country, like United States, you know, people in New York are not well mixed with people in Seattle. So there's no point in using a hypothesis like that for a whole population size of the United States. It works only for close-knit communities. This could be, for example, a good model for a small campus, residential campus, maybe. Then, in addition to that fraction of people you meet, lots of constant probabilities, which in practice, they're really constant, okay? So, for example, like I said before, the probability to be close enough, that may change dynamically. There's a news tomorrow that you have to social distance. Already a portion of the people change their attitudes and they maybe stay at more distance from each other. So then all of a sudden that probability is modified. Probability of transmission to occur, you put the mask on, that's also different, right? So I mean, lots of hypotheses built in from the beginning can change dynamically. And then if you want to incorporate that in the model, that becomes far more complicated. In this part, I want to go over another version of the contact rate. So this is what I basically derived here, this lambda SI, that's called homogeneous mixing contact rate, or mass action law. These are also used, for instance, in cell cell-based models, in which is quite reasonable. For instance, if you model interactions between microbes or viruses and cells, it might be reasonable to assume that the population, which in this case are virus particles or cells, are well mixed in the bloodstream, right? I mean, that's a reasonable way to put it. So what if the population is not well mixed? And in that case, we have pretty much, let's go a little bit faster on this one. So if the population is not well mixed, so if population when we go over that list on what you do, what you write from the point of view of one infectious individual, you can't assume anymore that an infectious individual meets a fraction of the total population, right? So that's not realistic because the total population is not well mixed. We go on your daily life, you meet basically the people you come up in contact with, but you don't have a chance to meet anybody in the population. So in that case, you can make a modification and say, I'm going to say that, and let's not call it F from fraction. Let's say little s, no, not s, because that's susceptible. So let's call it little a is the number of people an infectious or infected person meets per unit of time. So it's important to understand that unlike in the previous case when f was a fraction, this is an actual number of people per unit of time. Now, because if the unit of time could be very small, like in the matter of hours or minutes, this can still be less, I mean, on average, can still be less than 1. But in general, if the time is long enough, this could be actually a real number of people. So it typically is bigger than 1. On the other hand, you will see the contact rate is again further reduced by those reduction probabilities. So the probabilities are further reduced by, again, the probability of meeting a susceptible, and just like before, whether you are close enough, whether the transmission actually occurs, and so on and so forth. The crucial thing is that this is no longer multiplied by n of t. So when you write the contact rate, so you have I of t infectious people, and each of them causes that many new infections per unit of time. Number of people met per unit of time, probability of susceptible, close enough probability, probability of contact, of the transmission to occur. So when you collect again those constants, notice n of t doesn't cancel anymore. So instead of s times I only, you have si over n. And again, the math typically is harder in this case, especially if n is not a constant. If the total population is not a constant, which can happen in some cases. Now, in models, you can rename this again lambda, and this is called standard incidence. But it's important to understand that the meaning of lambda is quite different. And the main reason it's quite different is because of this constant here. This is no longer a fraction, but it's basically the total number of people per unit of time. So you assume that in a given day or a given unit of time, one typical individual meets a certain number of people. So for example, in a small campus, maybe that average number of people met in a given day is 5, 10, and so on. And you can see basically how they talk about super spreaders, or individuals that may be very efficient in transmitting disease, because it depends on whether you're an average individual. Nobody's an average, basically. That's one thing. But how far you are from an average, right? So maybe most people meet 5 people per day, but maybe a certain individual who happens to be infectious, goes to various events in a couple of days where he or she meets a huge number of people compared to the average. And so in that case, that single infectious person could be cause for a huge spread of the disease. When you put it in the model, this again is an average. I'm going to finish this part to emphasize that fancier models are usually a little bit more complicated than that, even far more complicated than that. It's not just standard incidence and homogeneous mixing. There are lots of versions in between. For a more realistic model, what happens usually, you will have essentially the contact rates. So in a more general setting, you will have the contact rates which ties up to this number of people you meet. You will have it a function of the individuals in the model. So for example, in a more general setting, suppose for instance you have susceptible, infected, right? You could think about the contact rate as some function C of Si that is multiplied by S over N and I. And then you can make assumption of this contact rate. So once again, I have I infected people. Each of them basically makes a connection with a certain number of people and then transmits the infection with various probabilities. All of these lumped into this function, and then the probability of meeting a susceptible S over N. So this probability of meeting a susceptible, you can always have it separated because it's always the same, right? I mean, no matter how fancy you make this contact rate with the number of people, then the probability that each of them is susceptible is S over N. But this contact rate here that incorporates these probabilities can be made more dynamic, because you can think about, for instance, let's say you have very few susceptible and lots of infected. So you can assume, for instance, that the population is more fearful, and then, or there is some self-quarantining measures. So people's attitude change in response to the epidemic. And in fact, I have some papers written on that topic. If you can take a look of my website if you want. There's a paper about risk-taking behavior, in which the contact rate basically is modeled to reflect the attitude changes in response to the epidemic. So this doesn't have to be constant. It can depend on lots of factors, including how the population attitude changes in response to the epidemic. And you'll see some interesting consequences of that. And in my opinion, that's the reason why actually basic models sometimes show these unrealistic outcomes and people lose faith in the modeling, because they don't really take into account the dynamic changes in these contact rates as time goes on. And by the way, no model is perfect, and but one of the reasons why it can provide predictions so far from reality is because of this oversimplification of using constants. Now, the purpose of this class is to learn the basics, so obviously we're going to stick to constants. But I should have mentioned, I wanted to mention this before we move on, especially in the context of the news of today with the pandemic. So in the last part, we're going to go back to the logistic model to see how actually this plays a role in a simplest epidemic equation. So stay tuned.